So the rate equation. What this does is relates the reaction rate to the reactant concentrations. So let's say we have the following reaction. So we've got two reactants A and B reacting together to form two products C and D. The rate equation for this would look like this. Rate is equal to, we just write the reactants, so that would be whatever A is and whatever B is. So the square brackets, remember that means the concentrations of A and concentrations of B. So the rate equation can be written as K times the concentration of A to the power of M times the concentration of B to the power of N. So M is basically the order of the reaction with respect to A. So if you remember from that last example we looked at, that's the order that we calculated from the initial concentrations. So it's the order of the reaction with respect to A, and N is the order of the reaction with respect to B. K is known as the rate constant. As I said before, the square brackets represents the concentration of A and B. So concentrations are measured in moles per dm cubed, but as you can see, this rate equation will be different depending on what the reaction is. So for example, if you had a reaction with 3 reactants, then it would be K times reactant 1 times reactant 2 times reactant 3. There'll be 3 values here. So that means the rate equation always changes. It's not just one equation you memorize. And also, when it comes to the units, because concentration is measured in moles per dm cubed and rate is measured in moles per dm cubed seconds to the -1, this rate constant has units that can vary. So in a question, you'd usually be asked to work out the units for the rate constant because it will change depending on what the reaction is. So our M and our N are known as individual orders, and the definition for that is the power to which a concentration is raised in the rate equation, so that will be M or N. You also have the overall order, which is basically both M and N added together, so it's the orders of everything added together in the reaction. So the sum of all the individual orders, or in this case M plus N. Okay, so now I'm going to show you how to work out the rate constant. And we're going to use this example that we looked at earlier. So working out the rate constant K, let me give you the steps. So the first step is to write out the rate equation. So you can only do that once you've figured out the orders of each of the reactants. So from this, we worked out that for NO we had order 2, for CO we had order 0, and for O2 we had order 0 as well. So if we want to write the rate equation for this, we would say rate is equal to K times NO to the power of 2, because we found NO to be order 2, CO to the power of 0, and O2 to the power of 0. Now anything to the power of 0 is just equal to 1, so if you multiply everything by 1, you can just basically cancel these out, and you get your rate equation, which is just this for that one. Your next step is to rearrange the rate equation and make K the subject. So that would be K is equal to rate over NO squared. Then your next step would be to use the data from the experiment, so that's the table that we've got, and sub in the values. So we need the rate and we need the concentration of NO. So if we look back at our results, you can pick any of these experiments, 1, 2, 3, or 4. Let's just pick 1 for now. So our concentration of NO is going to be 2 times 10 to the -2, and the rate that goes with that experiment is 0.176. So we sub in those values into our rate equation. So we can say K is equal to 0.176 divided by 2 times 10 to the -2 squared. And when you do that, you get an answer of 440. Okay, so if you remember, the units for the rate constant aren't always the same, they change. So our step 4 will be to find the units. And to do this, we need to use our rate equation and write down the units for each one. Try and write them down with all the mole per dm cubed combined together. So for rate, for example, we know that rate is moles per dm cubed seconds to the minus 1, right? So a good way to write it would be mole per dm cubed. Let's put that in brackets and put the seconds to the minus 1 outside the brackets. It's still the same thing, I've just taken it out. Then at the bottom, you've got NO squared. This is concentration, so it's going to be mole per dm cubed. Put that in brackets. We're combining all the mole per dm cubed and put a squared on the outside. The reason why I say to combine the mole per dm cubed is because you can just easily cancel them out. So because this is a squared, it means you have 2 mole per dm cubed at the bottom, you have 1 at the top, so you can cancel them out. So this cancels out with one of these, so you're left with mole per dm cubed at the bottom and seconds to the minus 1. And what you need to do is you need to bring all of this up to the top of the fraction. So this is the same as saying seconds to the minus 1. So instead of saying divided by mole per dm cubed, you can just say times by and flip the fraction over, dm cubed over mole. Because this is basically seconds to the minus 1 divided by mole per dm cubed. So if you want to write it a different way, you can just times it and flip the fraction. And then, because the mole is at the bottom of the fraction, that's essentially moles to the minus 1. So what you've got here is moles to the minus 1. Your dm cubed is at the top of the fraction, so that stays as dm cubed. And seconds to the minus 1 stays as seconds to the minus 1. So that's your units. So we've got our units and we've got our answer. So we found the rate constant. So the key thing with the rate constant is that the higher the value of the rate constant, the faster the rate of reaction. So that means that the higher the temperature of a reaction, the higher the rate constant, and the higher the rate of reaction. Okay, so now we're going to link this to mechanisms, rates and reaction mechanisms. So from organic chemistry, you should know what a mechanism is. It's something that shows the different steps within a reaction. So for example, let's say we had a reaction of A plus B going to products E plus F. So this is the overall reaction. But within the overall reaction, we have 2 steps. So step 1, the A and the B react together to form some intermediate products called the C and D. And then the intermediate products in the second step react together to form the final products E and F. Okay, so this is a 2-step mechanism. Now, every reaction has a different rate. So out of these 2 steps, one of them is going to be faster than the other. And what we do in this topic is we assume that the slow step out of the ones in the mechanisms is the one that defines the rate of the reaction. So let's say in this example here, step 1 was faster and step 2 was slower. So because step 2 is slower, we make an assumption that it's much slower. So when this reaction occurs, much more time is spent in step 2 compared to step 1. So the rate is determined more by what happens in step 2 than step 1. And we assume that step 1 is negligibly fast, that it happens so fast that it doesn't affect the rate. But for the slow step, you assume that the whole reaction is happening in the slow step. So we call this the rate determining step. And what you'll see is, because this is the one that affects the rate of the full reaction, is in your rate equation. So remember, your rate equation tells you how rate changes with concentration. In your rate equation, you'll see only the reactants in your rate determining step. So for this example, the rate equation would only have the concentrations of C and D in it. It would not have A and B in it, because that reaction happens so fast that it doesn't affect the rate, so it's not in the rate equation. So the overall rate is decided by the rate determining step, so only the reactants in the rate determining step will be present in the equation. So for this one, the rate equation would look something like this. Rate is equal to, so remember there's no A or B, there's only C or D because they're the reactants in the rate determining step. So K, concentration of C to the power of something, M, times concentration of D to the power of N. So this is how it would look like. Now to figure out what M and N are, you can use the numbers in front of each reactant in the balanced equation. So here, C has a 1 in front of it, D has a 1 in front of it, so C would be to the power of 1, and D would be to the power of 1. But if step 2 was 2C plus D, then the rate equation would say C squared times D, because D would be to the power of 1 because it's order 1 with respect to D. So we can say the individual orders M and N can be found using the balancing numbers in front of C and D in the rate determining step. So whatever number that C and D have in the equation to make sure that they're balanced. So to understand this better, we can look at a few examples. So let's say we have a reaction with the following mechanism. So a chlorine radical is reacting with O3 to form ClO radical and O2. Then the ClO radical is reacting with an O radical to form Cl radical plus O2. So in this question, they've given us 2 steps, and they've also given us a rate equation. So from this, you can work out what the rate determining step is and what the faster step is, because you can see that in the rate equation, we have Cl radical and O3. So that must mean that the rate is determined by these 2 reactants, and out of these 2 steps, the first step is the one that contains both of them. So that means the first step is the slow rate determining step, and the second one is the fast step. So you just look at which ones have the reactants in the rate equations. So if whatever is in the rate equation is in the reactants of your step, then it means that step is the slow rate determining step. If it's not, then it means it's fast. So in this example, step 2 would be the faster step because ClO radical and O is not in the rate equation. Okay, so another example. So we've got an overall reaction here. The rate equation is here, and it's asking us to suggest a 2-step mechanism. So here you need to kind of figure out the intermediate products, because you can only figure out the initial reactants and the final products from the overall reaction. So let's write down what we can definitely say. Because the rate equation has this molecule and a H plus in it, you know one step, whichever one is the slower one, is going to have both of these in it. So you know that both of these are going to be together on one of the steps in the mechanism. You can also say that one of the final products will be the product in the overall reaction. So that would be the CH3CO, CH2I. So now it's a case of figuring out the intermediate compounds. So if you add both of these together, this is an ion, it's just a H plus ion, it's just going to add on to the CH3CO, CH3. So what you're going to end up with is CH4 plus on the end, because the H is just attaching onto that CH3. That means this is also going to be a reactant in the second step, so we'll put it there. But if you notice in the second step, there's an I here. From the overall reaction, you can tell that there's an I2 somewhere on the left-hand side, because remember, the overall reaction is going to be both of the mechanism steps added together. So the I2 will probably come here, and then if you think about it, if you add I2 onto this, the H from the H plus can be added on to this to form HI. So we'll put that in. So now we've put in 1, 2, 3, and 4. And when you add both of these reactions, you should get that overall equation. So if we think about it, you have CH3CO, CH3 plus H plus. You don't want this in your overall reaction. They need to cancel out, which they do because you have this in the product side, you have this on the reactant side. So they cancel out. The I2 is also on the left-hand side. And then on the product side, we have CH3CO, CH2I plus HI. But if you compare the two, you see that there's something different between what we've just calculated and what we should be getting. There's a H plus, there's an extra H plus in our overall reaction. So that needs to cancel out. And that would come out in the second step here. So there'll be a plus H plus here. Because if you think about balancing it, you have 1, 2, 3, 7 H's here. You got 1, 2, 3, 5, 6 H's here. So you need an extra H here. So the H plus comes here, and that cancels out, that cancels out. So that means there's no H plus in the overall reaction, and your overall reaction is now satisfied. So the final answer would be this as step 1 and this as step 2. So getting rid of the crosses, that's how it should look like. For more videos like this, summary videos, worked examples and exam tips, subscribe to my channel.